at least a general rectangle there. Are you there? Shoot, I don't like that example. It was too easy. Well, you know what, you guys? I think I need a model in space.
Shouldn't the whole thing be in parentheses, not just
The
half
whole
of
thing.
it?
Oh, my apologies. I agree.
All right.
You know, when I sit here and make up examples out of thin air, I'm just not careful. I apologize.
Well, you don't have Eric here today, so I have to sub in.
You're learning bad habits.
Yep.
Well, you guys just tell me in words, what do I have to check? So am I looking at kernel or am I looking at range? Neither. I just look at the linearity properties to define a transformation to be a linear one. Did you guys see my point?
Yep.
So to show us, to see if it's a linear transformation, let's you and I take a peek at T evaluated at a sub naught, a sub 1, a sub 2, a sub 3, plus my b sub naught, b sub 1, b sub 2, and b sub 3. I think it's merely going to give me T evaluated on this one single 2 by 2 matrix, this one right here. And I know how to transform element M2 to the corresponding element P2. I've got the recipe right there. I think all I'm going to get is the very first entry as my constant term. I don't think I have a term involved in the variable x, but I do have an x squared term whose coefficient is the difference between these two entries of my matrix. Oh wait, I'm over here. So I meant to say the difference between these two entries will be the coefficient for x squared. I guess that gives me a1 plus b1 minus a3 plus b times x squared.
Again with the parentheses.
I just having so much issue with parentheses today. I don't like parentheses today. And I think that gives me this. Rearrange it by terms. I think it gives me this. But I think, shoot, I'm running out of room. I think this is nothing more than the transformation of the matrix A sub naught. A sub 1, A sub 2, and A sub 3. Plus this one. So do you guys agree it certainly is the case that it satisfies the first linearity property? And I maintain, if I were to take a peek at, can I call this a check mark? I check the first linearity property. So check mark. Check the second linearity property, all of IT, at this. Now, you guys, to see what this looks like, I've got to transform a 2x2 matrix that's clean. In other words, nothing on the outside. So let me transform this inside my parentheses to something clean. Be quiet. It's a single matrix. And I think that gives me this. Okay, I'll go slow.
C A sub 0, C A sub 1, C A sub 2, C A sub 3.
And we'll be here all day.
I like this
Anyway,
A's.
the point is, now when I transform, actually, I do want to slow down. I want you guys to be careful symbol by symbol. What should I write next? What should I write next? C A sub naught
Yeah.
plus 1.
Parentheses, C A sub 1 minus C A sub 3.
Okay, perfectly put. I agree. Or shall we say C A sub naught plus 1?
C parentheses.
Good. Pulling the C out. What should I say next?
A sub naught plus parentheses A sub
Perfectly
1
put
minus
again.
A sub 3 x squared.
Or shall we say this is just C times the transformation of this matrix, whoops, hold it, of this matrix with my A's. Ah, shoot, I've shown the second linear property. So I guess this is indeed a linear transformation. Anybody? What should we do first? I mean, how do I answer the question? I have to use one-to-one. What do I look at?
Find the kernel.
All I think I need to do is look for the kernel of this transformation. And I think, you guys, can I be long-winded about this? I might be writing too much. I think the kernel of my transformation is nothing more than a collection of all vectors in the first vector space. I even forget what the vector spaces are. All the v bars in M2, such that they get transformed to 0 in the second vector space, which, by the way, is what? Oh, the second vector space is P2, so that is a 0 element. You guys, again, I'm writing too much. I just want to make sure you understand what I'm trying to get at. I think I'm looking at all of the matrices, the A sub naughts, 1s, 2s, and 3s. Such that they get transformed over to the 0 element in the second vector space. Let me say that again. I think I'm looking at all these 2x2 matrices. I'm not going to change what I have. Such that when I transform them, and by the way, when I do transform them, I get this. You know what? I don't get this. I can't even read it. Somebody tell me how I made up this transformation. Was it A sub naught plus, I think, A1 minus A3? X squared, is that correct?
Yes.
Such that that particular output, the transformation of this 2x2 matrix, is equal to 0 in the second vector space. I'm not using a 0 bar sub W because I know what the element does look like in the second vector space. Oh, but shoot. I think what this is implying is I'm looking at all these 2x2 matrices. You guys, let's just cut to the chase. Such that A sub naught is equal to what?
0.
And A sub 1 is equal to what?
0.
I can't hear you.
Oh.
Negative
How about positive 3?
Oh, okay.
And I think it looks like this. These matrices, where the first entry is 0, the second entry is,
A sub 1.
Negative.
third entry is,
Or 0.
I
Or
heard
A
you
sub
say
2, yeah.
anything.
A sub 2. A sub 3.
Exactly.
Or A sub 1.
Shouldn't?
Yes, it should one.
But
Definitely. I was just-
you could technically just refer to the second one as A sub 3 and the
Yeah.
final one is A sub
Absolutely.
3.
Well, you call it-
They're
T.
interchangeable, right?
You can call
So-
these two T, call that one S, which was what you
Yeah.
usually do.
Okay.
Doesn't make any difference. such that a sub 1 and a sub 2 simply range over the reals. You guys, I'm running out of room? Maybe not. Maybe I can do this. But I think this is nothing more than a collection of all matrices that can be interpreted as the sum of this one with this one, such that A1 and A2 range over the reals. Oh, you guys think it's too sloppy. Can you just cut to the chase and tell me what's in the basis for this vector space?
0, 0, 0, 0, 0, 0, 1, 0, 1.
Awesome. Shoot, you guys, I blew it. I lost track of the question. What was the question? Is it 1-to-1? What's the answer? No. I think there's this note. Do you mind if I stop writing? Because the kernel is not, well, a little bit of writing. Because the kernel is not equal to the singleton set that contains a 0 in the first vector space, then I will proclaim that the kernel, then I'll proclaim that the transformation is not 1-to-1. How about another question? What is the dimension of the kernel? What is the dimension of the kernel?
2, but,
But what?
well, you don't have a kernel here, right?
I think I do. As a matter of fact, I just shown you on the import that this is the kernel of my linear transformation.
But it isn't 1-to-1.
Well, that's okay. Just because the transformation is not 1-to-1 doesn't mean I have a kernel.
Okay,
To say that the transformation is 1-to-1 simply means the kernel is that basic.
okay.
No pun intended. Very basic.
So then 2-dimensional, right?
It's two-dimensional, yes. All right, get sophisticated. Is this linear transformation onto? Is this transformation onto?
Dimension of the range is the same as our original vector space had dimension 2. The dimension of its volume is 2. So the dimension is just 2. No, it's not.
Well, the original vector space had dimension.
2, 1.
I think it's 4. Because aren't I starting from M2 going to P2? All right, everybody, here I go. I think you're correct that this transformation is not onto. Here's why. Because when it comes to dimension of the range plus the dimension of the kernel, it should be equal to dimension of the second vector. It should be equal to dimension of the first vector space, which is
4. Well,
But the domain of the dimension of the kernel is already understood to be
2.
2, so the dimension of the range is going to be
It'd have to be 2.
2. But if the dimension of the range is 2, and the second vector space has dimension 3, then that clearly tells me that my particular transformation is not an onto transformation. Do you see it?
Where,
If you don't, I'll write it.
yeah, I just want to see where the dimension 3.
This is
For
2,
the
of course.
range.
Can I write it all out?
Yeah.
Here's what I really meant. And again, you guys, this is why the general rank-nulity theorem is so important. It often helps me identify whether my transformation is onto. So, I think the dimension of the kernel plus the dimension of the range has got to be equal to the dimension of the first vector space. But you and I just found the dimension of the kernel to be 2. I don't know what the dimension of the range is. But certainly the dimension of M2 is going to be 4. But that necessarily implies the dimension of the range is equal to 2, which is not the same as 3, which is the dimension of my second vector space, which is P2.
Can you just show me how you got 3 for the range?
I didn't. I got 2 as the dimension of the range. I was just simply looking at the dimension. I'm
Well,
too sloppy.
Yeah, but or 3 is the dimension of P2, I guess.
Because you and I know what P2 is.
Okay.
Collection of all elements of the form a sub naught plus a sub 1x
Okay. Okay.
plus a sub 2x squared. Therefore, it clearly has dimension.
Yeah.
Therefore, T is not onto.
When we defined onto, we said that the range of T has to be equal to the W. Like if we had gotten that
Yes.
3 equals 3, does that imply that it is now onto? or-
Always, because I think a domain or range is equal to 3. Given that you and I have already proven that the range of T is necessarily a subspace of P2, the fact that it's a subspace and it has the same dimension as P2 means it has to be all of P2. Could you guys comfortably, what, never mind, could you comfortably, I messed up, didn't I, with my numbers, is this part 3?
Yeah.
My apologies, I didn't number it. Okay, on to part 4. Could you guys tell me comfortably what this is? Not its dimension, I'm asking you exactly what's in the range. What do those entries look like? By the way, they're going to be elements of P2. Anybody at all? I'll rephrase the question. What the heck do all these transformed 2x2 matrices look like in the second vector space? Go back to exactly how I first defined this linear transformation. All right, it's a sub naught plus a1 minus a3 x squared. Or how about saying they're nothing more than the a sub naught plus a sub 4x squared is. Or a sub naught and a sub 4. Range over the reals. Oh, you guys, I don't like it. That's too clunky. Can you rephrase this? I think this is nothing more than the span of, help me with this.
1 plus x squared.
Well, we're running out of time. Are you okay? Daniel, well,
Because that would imply then that the coefficient in front of the 2 is always the same.
yeah, I think I'm wrong for a lot of reasons. Daniel just said, this implies a constant term saying it's a coefficient of x squared. Here's another problem. You and I just found the dimension of the range to be 2. I think the dimension of this vector space is 1.
One.
Did you guys see my point? So I think to fix my mistake, I'm gonna,
Make a comment.
yeah, replace a plus with a comma. Now I've got 2 elements in the range, which makes sense to what I found up here with the general nullity theorem, and I think it makes a lot of sense relative to what I have above it, because look at that, 2 free variables. All right, no tricks this time. Yeah. Oh, I get to take my board space back. Except for the
Top of the middle.
no, I can't think of it. All right. Oh, yeah.
Where are you going? Top of the middle. Maybe some section.
I gotta work.
We should move.
I really need to find
Yeah,
a
let's
day
do it.
here that I can get into study. I can do it Thursday afternoons.
There's just work better for me easily. Was this assignments to do the lab.
Me too. All right. I'll be in here tomorrow afternoon. I'll stay all afternoon and study. Because, yeah, I'm falling behind. I need to start doing that, but they likes to schedule me in the afternoons. I'm probably gonna go in there and snake some food though.
So you guys, nothing dramatic, it's just a bit of actually, I take that back, it is dramatic. But as far as this definition is concerned, I'm just giving a name to a linear transformation that has to be one-to-one and onto. And if I got a one-to-one onto transformation, I will say that that linear transformation is an isomorphism. Sometimes I'll say it's an isomorphism from V to W. But if I got a one-to-one onto linear transformation, then you guys take a peek at this general nullity theorem. Dimension, kernel, plus the dimension of range is equal to the dimension of the first vector space. But if I've got a one-to-one onto transformation, doesn't that suggest that this is equal to this number is equal to 0. And if this really is the case, I'm sorry, I can't speak today, my apologies. If this really is the case, what does it say about the range? Well, no dimension. What does it say about the range itself? Well, the range is equal to the... Well, not V. I think that if T is onto, it means the range is equal to... But I didn't mention dimension. I'm just asking what the range is equal to. You guys, my definition of range is
Transformation.
just the second vector space. Everybody? Wasn't that my definition?
Yeah.
You're making me nervous. So I guess a T is onto, the range is nothing more than W. Oh, but shoot, you guys, look what this says. It says that dimension of V and dimension of W are the same. And if those dimensions are the same, it means they've got the same size, and it means I can go back and forth from one vector space to another quite easily. As a matter of fact, let's see if you and I, without any effort whatsoever, let's see if you and I can create. What number am I on? 4?
Yeah. 5.
Oh, is it 5? Yeah. Let's create an isomorphism. From, for example, I don't know, how about P2? R3? Anybody? Could you just make up a linear transformation out of thin air that's an isomorphism? Very basic linear transformation that's both one-to-one and onto. Do you think you can create an isomorphism from R2 to the complex numbers? I know you can do it. Could I have written A1 plus A naught on? Of course I could. That would just be a different isomorphism. It would work.
Those are not the same.
What's that?
Oh, never mind. Sorry, I misread. Because they don't have the same.
Oh, you know what, you guys, I'm using too much ink. You know what I really could say? That when you look at A sub naught comma A sub 1, it's basically the same as a complex number. Which is basically the same as an element of P1. Which is basically the same as two-dimensional vectors you had back in trigonometry and in physics. It's all the same game. I can create isomorphisms from one vector space to another, which means, in disguise, they all represent the same underlying vector space. And as of now, I guess I can make this proclamation. Any vector space of dimension n can be transformed into nothing more than Rn. I can always find an isomorphism from any n-dimensional vector space to Rn itself. So I guess everything I've told you so far in the book is kind of silly, in the sense that everything reduces down to Rn if it's an n-dimensional vector space. I will always be able to create such an isomorphism. I've got more to say, because I really want to talk about undoing transformations, but I think I said a lot today. Can I be really picky about the homework? Only because I'm kind of jumping around just a tad bit right now. So allow me to be picky, so you guys can get started all the time.
Can you maybe
Yes.
tell us what the test is going to be on next week?
Is it next week already?
Yeah.
It's coming up fast.
I'm sorry, I'm really shocked. I've had a really bad week, so a couple weeks. So our exam next week officially starts at 4:05. Guys, I'm sorry, this is still today's Wednesday. Tomorrow's Thursday. How about just stopping? In 5-6.
5-6?
So stopping at 5-6.
5-6. Okay, how much of 5 are we gonna be doing? Or can you maybe tell me, like, which parts of chapter 5 we're gonna do? Just so I can take a look at it.
All of them, 5-6.
Every single thing in 5, every single
Well,
chapter?
I think it's 5-6.
Okay.
I don't know, haven't thought about it.
And, after we're done with, rank and nullity, is that everything out of 4?
I'm gonna come back and talk about the inverse matrix.
Okay,
But it's nothing you really have to worry about for the exam.
okay.
What do you think about 412, advanced class quiz? Are we ready to start up by taking quizzes again?
Yes, please. Is there gonna be a, Saturday session this week?
Yeah, I think we're ready.
Okay.
I think we have enough behind us, Brian.
Okay.
That-
Saturdays.
You can do it all.
No, what?
You can't do it all.
No.
Sorry.
Always something.
How long are you guys gonna be in the, math center for?
Couple hours.
Probably an hour to an hour and a half.
Yeah.
So then I get off work at 4. You guys
Yeah, I-
probably gonna be out of there, or, huh?
I have a meeting at 4. I'll be
Okay.
at that. We're thinking about moving to Thursday, would you rather do it?
Yeah.
Thursday I have the entire afternoon open.
Yeah, I think
That would
Thursday's
be
works
great
best
if
for
you guys
everyone.
can do that.
Yeah, Thursday.
That'd be nice.
Because I mean, I really need to get in on some of these study sessions. I'm
Yeah.
losing out because I'm always down there working. I got my hours cut a bit, but he likes me in the afternoon, so.
What do you do?
Huh?
What do you do?
A tutor.
Too? Oh,
Math
nice.
PE,
Yeah.
stuff like that.
Alright, cool. Well,
Thursdays, starting next week, we'll do Thursdays.
All right, awesome. I'll be there tomorrow too. If you guys are there.
I'll be there.
I don't know.
Yeah, well, you can't hate the pink fluff ball.
Oh. I should be writing down homework. You don't mind if I come and snag some of your food though, right?
Not at all.
Alright, awesome.
There's plenty of food.
The only thing that let me short on is bowls. I can
Yeah.
only bring 4.
I didn't bring any plates. I brought 4 because I brought 3.
Oh,
I brought
Oh,
6.
you guys, I typically have stuff in my office.
Oh, yeah.
you have plates in your office?
Yeah, what do you,
Oh, plate, maybe a fork?
Bowls.
I don't know
utensils.
bowls.
Utensils?
Plates?
I've got some utensils, I don't know what they are.
Okay.
I'll bring them in the mess.
Do you have to have a microwave in your office?
I've got one right outside the office.
I have to
It's
go
just
all
before you
the
go
way
to my office. It's a little, it's just right above the printer. You'll see it.
Nice.
I'll get us a
Alright.
table.
Alright.
And if somebody has to
No, I
say,
got-
Professor Ballack, I
What?
already do this for the,
Middle back.
Did we really go through all of
Yeah.
this today?
well, for the last 2 days.
2 days.
Over the last 2 days? Wow.
Sweet.
Isn't the rank and nullity chapter, isn't that, in 4?
Yeah, I just
So
mentioned it
it's over
because I
the-
think the general rank nullity theorem is more.
Okay, but there's no homework from that chapter though?
I care not once,
4
whatsoever.
sections more.
But this will be.
Would it be beneficial to go through and do some of the problems in that
I just
chapter?
wanted to-
Very
you know,
minute.
it's all gotta be
Huh?
done before
Very
Thursday,
minute.
right?
Minutely, alright.
15? 16?
Oh, the heck with you guys, have just one exercise in there, just to get a feel for it, and I'll assign more tomorrow. The other problem with me assigning things in 5-4 is the author puts in there something about inverse transformations as well, with most of the questions, and I haven't mentioned that yet. We'll get it tomorrow. Thanks for your patience. Oh, I took it back, we're done early. Geez, so where are you?
Yeah.